So we're doing 5.4, Fundamental Theorem of Calculus. With that name, you would think that this was going to be a really important theorem, and you're right, it is. It's a really important theorem. There's actually two parts to it, and it looks really kind of confusing at first. But basically, part one is going to say that as long as you're dealing with functions that are continuous, that the integral and the derivative are inverse functions, backwards and forwards of each other. Specifically, it says that if you have the integral, and you call that capital letter F, is what you get when you integrate, that when you turn around and take the derivative of that, well, since you're taking the derivative of the integral, you would expect just to get your function back. And that's pretty much what it says. We'll go into more detail in a couple slides here. The second part to the fundamental theorem is basically telling us how to evaluate an integral, and we actually were doing this in the previous section some. So again, you have to make sure that you have a continuous function everywhere that you're looking at. But if I'm thinking of this as how much area is under the curve of the graph of f between x equals a and x equals b, then I find the antiderivative of this function, and that's what I call capital letter F, and I just plug in the upper limit minus and then plug in the lower limit. That's how I evaluate it. And like I said, we were doing this actually a little bit in the previous section. Okay, so for starters, I threw in a couple examples here. So this is our original problem. It's just straight up find the integral. In this section, they're going to give you ones that make you think just a little bit harder on what the antiderivative is. Again, in this chapter as a whole, all of chapter 5, we don't really get any great techniques for finding antiderivatives. They really just ask you to kind of think of the opposite of your derivative formula and try to kind of work it out in your head. When we go on to chapter 6, we're going to get some techniques. So if the function here is a pretty complicated looking function, then we have some techniques. But for this section, you should be able to look at it and go, okay, if I can reason out what the opposite of the derivative is, that's going to get me through this. So here we have a constant raised to a variable. This would be, if you think back to derivatives, it was a to the u. And the derivative of a to the u was 1 over ln of a to the u du. And so, it was a to the u times ln of a. So the opposite, instead of multiplying by ln of a, we're dividing by ln of a. So again, a to the u, the derivative formula was a to the u times ln of a times derivative of the exponent. So instead of multiplying by ln of a, we're going to be dividing by it, or multiplying by 1 over it. Okay, so this is my antiderivative. And then my limits go from 2 to minus 1. So bottom number 2, top number is minus 1. I plug in the minus 1 first, subtract, and then plug the 2 in. I left the 1 over ln of 3 out in front since that's just a constant. There's no variable in there. So I just pull that out in front. So I plug in the top number minus, plug in the bottom number. And I simplify this all the way down, and then a nice little decimal here at the end. At the bottom of the screen there, at the bottom of the screen, I went ahead and wrote out what you would need to type into your TI-89 if you were going to do this on your calculator. So n-int is numerical integration. You would type in your function that you're trying to integrate, comma, the variable that you're wanting to integrate with respect to. In this case here, you see a dx. So we put an x there, and then you always put the lower limit, comma, the upper limit, and that would give you the same answer, negative 7.88. Okay, my other example here, the integral. Oh my goodness, I keep doing that. Okay, for this one, this just goes to show that you want to simplify things algebraically first whenever possible. So if I put 1 over root u, that would give me u to the negative 1/2, and then I'd have root u, anything over itself is 1. So I just algebraically simplified it first, and then go ahead and do my antiderivative, my opposite of derivative. So I do power rule, reverse it, so add 1 to the exponent, u to the positive 1/2. Divide the coefficient by the new exponent, so 1 divided by 1/2 is giving me 2. And then the 1, I also do the antiderivative of that, so it must be a u because the derivative of u is 1. And I go from 0 to 4, plug the 4 in first, minus, plug the 0 in, everything seems to go away, I get 0. And so again, if you wanted to enter it in your calculator, if you have TI-89, looks like this. By the way, the TI-84 will also do the integrals on, as long as it's a definite integral, like you have a number here and a number here. On the bottom and the top of your integral sign are just actual numbers. Your TI-84 will do this as well. Okay, so for this one, it's asking for total area between the curve and the x-axis. It's a cubic. I can tell if I factor x out of this function, I'd have x times x squared minus 4. So I know it's going to go through the origin since x is one of the roots there. So anyway, I went ahead and graphed it, and sure enough, between minus 2 and 2, I can tell that it's going to be nice symmetrical. There's the same amount of area above the x-axis under the curve as there is below the x-axis above the curve. So I could just find one section here and double my answer, or I could find each section separately and make sure that this part down here, which would come out negative, I have to remember throw absolute values on it and make it positive. Oops. Okay, so I break it up from -2 to 0, since that's the part that's above the x-axis, and from 0 to 2, since that's the part that's below the x-axis. And then again, my antiderivative, add 1 to the exponent, divide the coefficient by that new exponent. Same thing for 4x, add 1 to the exponent, so it's x squared. Divide the coefficient 4 by the new exponent 2, so 4 over 2 is 2. And I look at my limits. This is, of course, the exact same function, so same antiderivative, just evaluating it on different limits. And I get 8. So again, if I look at this first part over here, I didn't really need absolute values. That's the part between minus 2 and 0 that's above the x-axis anyway. So of course this comes out a positive 4 anyhow. But the second term over here is really the one that I need the absolute values on. So from 0 to 2, it was below the x-axis. It turned out when I integrated it, I got -4, and so the absolute values makes it positive 4. Okay, so that is looking pretty similar to what we did in the last section, 5.3. Okay, let's move on to the fundamental theorem again, part 1. Let me flip back here to the very first slide, here where it gave my fundamental theorem. So part 2, we've already done a couple examples of. Let's go back and look at part 1. So part 1 is the part where they're really focused in on saying that derivatives and integrals are inverse functions. So if I have some function here and I integrate it and then I turn around and take the derivative of it. So here again, I start off with some function, I integrate it, I get something, I turn around and take the derivative of that. What I'm expecting to get out is really just the function. If you think of inverse functions, that's always true. So if I have, let's say, x, and I take the cube root of it, and then I turn around and cube it, I get x back. Well, again, x cubed and cube root, those are inverse functions. Okay, so the only thing that's a little bit tricky is you have to watch your limits on your integral. So the bottom limit is a and the top one is x. A stands for any constant. I don't care if it's positive or negative or just irrational, rational, whatever it is. It's just some number. Okay, the top there is x. That's your variable. Okay, so when I look at my final answer, notice that it's not f of t that I'm getting back, it's f of x. So whatever that variable on top is, would end up, if you think of kind of the part B of your or part 2 of your fundamental theorem, because you're plugging in the top number minus plugging in the bottom number, you're really plugging in that thing on top. So this x gets plugged in place of the t, and so you end up with f of x instead of f of t. Maybe that's something we'll look at a little bit more closely in class. But anyway, you will get your function back just with the x plugged in. It gets a little more complicated though if that upper limit, let's say, isn't just x. What happens if it's x squared or 2x or something like that? Your chain rule comes into play again. So I'm going to drop down to where we were in the PowerPoint, right here. Okay, so again, it says for part 1 of the fundamental theorem of calculus, FTC, the a has to be a constant, and then the x up there, if it is just x, then you just get f of whatever x, you plug your x in. So there's a couple tricky things going on. So one is you have to remember from the previous section, if your integral limits are flipped over, meaning your variables on the bottom and your constants on top, you want to flip them over and make sure that you remember your negative happens when you flip over your integrand. Okay, so that's kind of just from section 3, 5.3. But again, what I was saying, if your constant's on the bottom, great. But on the top, let's say you don't just have your variable, you have something where the derivative of it is not just 1. So here the derivative of 2x cubed would be 6x squared. So you're going to get f of 2x cubed again, but then you're going to have to remember to multiply by your chain rule. And again, your chain rule is the derivative of that upper limit there, so 6x squared. And again, if you want to think about it as kind of your chain rule, you'd be taking the derivative of, again, this first thing is what we would call y. So you would take the derivative of y, and then you have to remember if this was u, you end up taking the derivative of u as well. Like I said, I think maybe we'll do some examples like that in class, in a day or so. So the last case here is the most complicated of all. So let's say on the bottom here, you don't even have a constant there. Instead, you've got something with your variable on the bottom and something with your variable on top. So again, you're going to have to kind of think about this as area under the curve between this value and this value on the x-axis. So hopefully this is going to make sense. If I take from 0 to the upper limit and I subtract from 0 to the lower limit, I will actually get from the lower limit to the upper limit. And again, if you want to be thinking of it as how much area is under the curve, if you picture 0 and then 2x and then 3x cubed, if I go from 0 all the way to 3x cubed and subtract off from 0 to 2x, then what's left is the area between the 2x and the 3x cubed. So once you make the translation, rewriting this integral as being the same thing as this difference here, then I can go ahead and use my fundamental theorem part 1. So from constant to the variable here, this is going to be my function with the 3x cubed plugged in, and then chain rule times the derivative of that upper limit. Minus, and then this part here, use my fundamental theorem again. It'll be my function with the 2x plugged in, and then again times chain rule, derivative of the upper limit is 2. Okay, let's try a couple of these. So I started off with the simple one, the first case. So here I want my constant to be on the bottom instead of on the top. Okay, so going from 1 to x instead. So I want to flip it over, 1 to x. Remember, you have to put a minus sign out in front. The question is asking not just evaluate it, but find the derivative of this. So the derivative of the integral, remember you just get your function back, only with the x replacing the t. So my minus sign is there, and I have 1 over x instead of 1 over t. Okay. Getting more complicated now. I don't have a constant on the bottom. I've got a variable, something with a variable on the bottom, something with a variable on top. So I'm going to have to split this up into the difference. So again, if we go from 0 to the cosine minus 0 to the sine, that should be the same thing as the area between sine x and cosine x. And then I'm going to take the derivative of each of these integrals separately. So my fundamental theorem now part 1, derivative of the integral should just give me my t squared back, only I'm plugging in cosine x in place of t. So I get cosine of x squared. And then I have to remember the derivative of cosine is negative sine. So here's my t squared part with cosine of x plugged in. So instead of t squared, it's cosine x squared, chain rule, times derivative of cosine is negative sine. Minus, and then same thing over here. So sine x gets plugged in, so I have sine x squared, and then derivative of the sine x is cosine x. And from there I just simplified it. Okay, I hope all that was pretty clear. Here's some practice problems. I would suggest you go ahead and hit the pause and work these two out, and when you think you have them, hit play, and I have one more slide showing the answers. Go ahead and pause. Okay, uh-oh. Hold on a second. I'm supposed to have one more slide. Just a second. Okay, so here's my two answers. The first one, just to straight up evaluate the integral. It's not derivative of the integral, it's just evaluate it. So I have to remember antiderivative of cosecant squared is negative cotangent. Derivative cotangent is cosecant squared. And then plug in top number minus bottom number, go to unit circle, evaluate. On the other one, this is derivative of the integral. So again, I'm expecting to get cosine of t back, only I have to replace the t with 2x. So I get cosine of 2x. And then derivative of the exponent is 2. Again, the angle is not being multiplied by 2. The whole thing's multiplied by 2. So it looks better when I put that 2 out in front. Hope this was helpful to you.